Hello, welcome back to Physics 211. We have been talking about moving charges or currents, and now we're going to look more specifically at how those currents can be organized as circuits. So we're going to look at some circuit diagrams of some basic circuits with batteries and resistors and capacitors, and then we'll look at how the current goes around those circuits and how the voltage drops around the circuit. Then we will look at the power that is dissipated by the different loads within the circuit. And then we'll also look a little bit at the energy in the circuit. So first of all, we're going to start by looking at this very simple schematic that we have here. And in this schematic, we can see that we have a resistor that is connected to a battery, to the positive and negative end of a battery. And it's also connected to both sides of a capacitor. And this resistor, we see that it even has the markings telling us, those colored markings right there, tell us what the resistance actually is. So this is helpful. We see exactly how things are connected, but it's even better if we can then take that and put it on a very simple diagram. And so the diagram that we put it on is this diagram right here. This is called a circuit diagram. And so over here on this side, it's typically where we will put it. This will be our battery. So this indicates the battery, where we have the positive terminal on this side and the negative terminal on the other side. And then our resistor, which we saw was connected to directly to both the positive and the negative sides of our terminal. So that's why it is drawn right here, where it's connected to both the positive and the negative sides of the terminal. And the capacitor was also connected directly to both the positive and the negative sides of the and then to the negative side of the battery. And so this is a circuit diagram of the exact same circuit. And a circuit diagram is just a logical picture of what is connected to what. So we can use different circuit diagrams with different elements of them. So here's a listing. We can look here. We've got the battery that we just saw. The battery looks like this. A wire is just a straight line. The resistor is this kind of zigzaggy pattern. And a light bulb will look something like this. It also has a resistance. It's a load on the circuit. We can also have junctions. In that case, they're just the wires, when they come together, they're just drawn as lines connected to each other. As we saw, we can have a capacitor. We just have two lines separated by a space. And this is a switch. So a switch means that when it's open, there's no current flowing. And when it closes, now the circuit is closed and we can have current flow. All right. So circuit diagrams replace pictures of the circuit elements with symbols. So let's look specifically at the symbol of a battery. So here's the symbol of a battery that we just saw. And what we notice is that there's a longer line on one end and a shorter line on the other end. This longer line is the positive terminal. The shorter line is the negative terminal. The battery's EMF is shown right next to it. It's usually written right next to it, the number, the actual value of the EMF. And then we also have the plus and minus symbols. Those aren't always there. Sometimes you just need to know the longer line is the positive terminal and the shorter line is the negative terminal. Now let's review two of Kirchhoff's laws and see how we can apply those to our circuit diagrams. So the first of those laws is Kirchhoff's junction law. And Kirchhoff's junction law just basically says whatever goes in must come out of our junction. So if we have a current going in, the total currents going into this junction must be equal to the total currents coming out. So in this case, we have I1 is going in and I2 and I1 are going out. So the junction law would tell us that I1 must be equal to I2 plus I3. So for a junction, the law of conservation of current requires that the sum of the current going in must equal the sum of the current going out. This basic conservation statement is called Kirchhoff's junction law. Now, we also looked at a second law that Kirchhoff has. Kirchhoff's second law is his loop law. And the loop law tells us that if we go all the way around our loop, the change in the potential as we go all the way around the loop must come back to zero. The total change in the potential must come back to zero. This is basically just saying conservation of energy. If we start at this point, we have some potential energy because let's say that there was a battery that moved up the charge escalator. So we have some potential here. And so as we go around the loop, we must end up back at the same with the same potential energy. So that's why as we go around, the change in the potential must equal zero. So we're going to add the potential differences around the loop, and we see that all those potential differences must equal zero. So in words, for any path that starts and ends at the same point, the change and the difference in the potential around the whole loop, the sum of the differences in potentials over the whole loop must equal zero. So the sum of all the potential differences encountered while moving around a loop or closed path is zero. This statement is known as Kirchhoff's loop law. All right, let's look at a basic circuit. So here we have a very basic circuit. So the most basic circuit that we can have is going to have a battery, right? Here's our battery, and a resistor. Which is written here as a load. So as I mentioned earlier, if you have anything that's drawing on the circuit, we call that a load. So it could be a light bulb or it could be a resistor. So here, the most basic electric circuit is a single resistor connected to two terminals of a battery, so connected to the positive and the negative terminal. And here is what that circuit diagram would look like. Here is our battery, and here is our resistor. And so figure A shows the literal picture, the schematic of the circuit elements and the connecting wires. And figure B is the circuit diagram. So one thing that we notice when we look at this circuit is that the wire starts if we look at the positive end of the battery, and there are no breaks anywhere in our wire. It is always connected. And so since it goes in a full circle and there are no breaks anywhere, what we say is that this is a complete circuit. So this is a complete circuit that forms a continuous path between the battery terminals. So let's try to look more specifically at this circuit diagram that we've just drawn right here. Let's look more specifically at this circuit diagram and see if we can analyze it a little bit better. So the first step that we just did was we drew the circuit diagram. And now, based on the orientation of the battery, we see we have a positive terminal on this side, our negative terminals on the bottom here. And so we know that the current capital I, is going to move in the direction that positive charges would move, even though we know it's actually the electrons that are moving. And so in that case, it's going to move from the positive terminal to the negative terminal. So the thing that we notice here is that we can draw our current moving as it's drawn right here, clockwise in a clockwise direction. Now, the next thing that we know is that on this side, as we move our charge up our charge escalator, it's going to have a change in potential due to the battery. That's what the bat is here for. And that will be a positive change in potential. We're going to move it up the escalator. We're going to take our charge and move it up the escalator to positive, to higher potential. And so that will be a positive value. So the change in the potential as we go across the battery is positive. Now, if we look over here at the resistor, we remember Ver. So Ver tells us that the change in the potential, the magnitude of that, is equal to IR. However, in this case, when we go across our resistor, we are going from the positive to the negative side. And so we are actually losing potential as we go across the resistor. So the change in the potential across a resistor is a negative value. We're going to be losing potential as we go across the resistor. All right. So the next thing we want to look at is our first light bulb puzzles. This is light bulb puzzle number 1, the first light bulb puzzle for the chapter. So this figure over here shows 2 identical light bulbs. So here are our 2 identical light bulbs, light bulb A and light bulb B, and they're identical. And the question we want to ask is, which light bulb is brighter? So if we want to know which light bulb is brighter, we might think that light bulb A would be brighter because it gets the current first, right? We see that the current's going this way around our circuit. And so if the current's going that way, then light bulb A should get the light bulb first. It should get the current first. Maybe it uses up that current. But then we remember Kirchhoff's junction law tells us that the current that goes in must come out. So whatever current goes into A must come out of A. So this is the same current. And whatever current goes into B comes out of B. So this is the same current. So because there's no junction of any current going off in some other direction, the current must be the same. So the current through both bulbs is exactly the same. So what we can see from this is that even though light bulb A gets the current first, it doesn't use it up. It's not the current that the bulbs use up, it's energy. And so what we see is that the battery is creating a potential difference. It's creating a potential difference, which supplies potential energy to the charges. As we move those charges up here, they get a potential energy equal to Q, the charge, times delta V. And so as the charges move through the light bulbs, they lose some of their potential energy, transferring the energy to the bulbs. Now, if we look at this potential energy that we have as we're that is going through that we get from the going up over the charge escalator in the battery. And we want to think, let's take this idea and use it to figure out what kind of power we're getting from the battery. So this is the potential energy we're getting from the battery. So the potential energy is Q delta V. And if we want to get the power supplied, well, that's going to be the energy over time. So that's going to be du dt. And so that will be dq dt times delta V. That's not really changing, but the charge is changing. And we know that this dq dt right here, that is equal to I. And so we see that the power, this is the power here, the power is equal to I times delta V, which for our battery is equal to I times the EMF. So if we want to see the power supplied by a battery, we see that the power is equal to the current I times the EMF. Let's think about what this means in terms of dimensional analysis here to figure out the units. We know that current is amps, and amps are also coulombs per second. So we have a coulomb per second in terms of units, times the EMF, which is a voltage. So volts are also joules per coulomb. So we can cancel out the coulombs, and we see that the power, the units for power, are joules per second. So the units of power are joules per second, and that is equal to a watt, which is a joule per second. Now let's think about the power dissipated by the resistor. So the power dissipated by the resistor is dissipated as thermal energy as the resistor gets heated. So that means that if we want to look at the thermal energy over time, that'll give us the power dissipated by the resistor. So the power dissipated by the resistor is going to be the change in the thermal energy over the change in time. Now we know that that must be equal to the power from the battery, and so that the power that's dissipated is going to be equal to that change in the potential energy as the energy dissipated will be equal to the change in the potential energy. That's where it's coming from. So we know that the power dissipated by the resistor will be equal to the change in the potential energy over the change in time. And we know that that is the same as dq dt times delta V. So the power dissipated by the resistor is equal to dq dt times delta V. And we know that this dq dt right here, dq dt, that is the same thing as our current I. So the power dissipated by the resistor is equal to I times V. Now let's look at, we remember that V equals IR. We remember our Ohm's law, that delta V equals IR Ver. So I'm going to put an IR right here. And so I can say this is equal to I times IR, which is just I squared R. Another thing that we can say is if I look at the same equation, right, if I look at the same Ohm's law, I can also rewrite this and say that I equals V over R. So I can write this equation as well as delta V over R times delta V, which is just equal to delta V squared over R. So in terms of the potential drop across the resistor, we can say, first of all, P equals IV, which also equals I squared R, and that also equals delta V squared over R. All right, let's look at the power dissipation in a resistor on a micro scale. Let's see what's going on in terms of the atoms and the electrons. So here is a really blown up image of the wire. And we see that in here, we have, of course, an electric field that is giving us our current. And the electric field will have the electrons moving in the opposite direction of the electric field. So our electron current is going the opposite direction from the electric field. And it's causing them to move and speed up because there's a force. It's applying a force on our electrons equal to the charge of those electrons times the strength of that electric field. And so that there is an energy. The electric field is causing the electrons to speed up. So there's an energy transformation from potential energy to kinetic energy because they're moving, they're speeding up, they're going faster. And so we know that the electron current is going in the opposite direction from the electric field. And of course, the current that we've defined as our current is going in the same direction as the electric field because it's going in the direction that positive charges would flow. Now, as the electrons are moving around inside the wire, they are colliding with the atoms and they're transferring energy to the lattice. So they're bouncing off those atoms and they're transferring the energy. And so this energy transformation is from the kinetic energy of those electrons moving around to the thermal energy as they bounce off against all these different atoms. So what we see is that a current carrying resistor is going to dissipate the power as thermal energy because the electric force is doing work on the charges. All right, so let's think about, we said that power is in terms of watts. So here, the product of watts, which we said watts, of course, is a joule per second. So a joule per second. So the product of a watt, which equals a joule per second, times a second, we'll cancel those. And we see that we end up with joules, which is the SI unit of energy. However, when you get your electric bill, it doesn't say anything about joules on it. So most electric companies prefer to use the kilowatt hour. So instead of watts times seconds, they're using kilowatts. So 1,000 watts times an hour, or 3,600 seconds, to measure the energy you use each month. Let's look at an example of that. If we have a 4,000 watt electric water heater, for example, and we run it for 10 hours, well, that would be 40,000 watt hours or 40 kilowatt hours of energy. if we have a 1500 watt hair dryer and we use it for 10 minutes, well, that's 1/6 of an hour. And so that's 250 watts or 0.25 kilowatt hours of energy. Now, I just looked it up today. So on Google, currently at the moment, it says that the average cost of electricity in the United States is about 12 cents per kilowatt hour. And that's about what we're paying right now for our kilowatt hours, our energy that we're using every day. All right, this has been an overview looking at circuit diagrams and how we can indicate batteries, resistors, capacitors, light bulbs inside our diagrams. How we can then see how the current moves through those diagrams, and how we can see how the voltage changes as we move through the circuit. And we can see that the total change in the voltage must be a total of 0 if we go all the way around our circuit.